And for most of us, when you learn a second language as an adult, you would never get to level 5. You wouldn't be able to understand this other language without having your brain fully focused on it. So what mean opinion score are we shooting for in the telecommunications business? 4. Not 5, but 4. And this is referred to as toll quality speech, and that's the benchmark that is used in the public switch telephone network, is coming up with a mean opinion score of 4. The coding technique for digitized voice shows up near the top of our list of things that affect voice quality. This is implemented with a chip, usually called a codec, which stands for coder decoder. And what this is an algorithm, a particular mathematical operation that is performed on the raw output of the analog digital converter. In traditional telephony, we use a technique where we take the output of the analog digital converter and code it into a range of 256 steps of value. And we take samples of the value 8,000 times a second. And then to code the value of the sample, that's a number between 0 and 255, that requires 8 bits. So in traditional telephony, what we end up doing is transmitting 8 bits, which represents the value of the sample, 8,000 times a second. So if you want to do the math to figure out how many bits per second that is, 8 8s are 64, it works out to 64,000 bits per second, second after second, minute after minute, hour after hour during your phone call. This was originally described as PCM, pulse code modulation, in some of the articles in the Bell System Technical Journal in 1947 and 48, when this was first described by Claude Shannon. So still some people call this PCM, but that doesn't really mean anything. PCM describes the general idea of doing voice digitization and coding. The more accurate way to refer to this is to call it a DS0, Digital Service Level 0. So we've all heard about service level agreements with telecommunication carriers. This was service level 0, the basic idea. It's one phone call, it's one trunk, it's one channel, 64 kilobits per second. Now there are standards for doing that in the Bell system, and they become Bell Core standards after AT&T was broken up. When we're talking about voice over IP, we end up talking about ITU standards for doing the coding. And these are the G.700 series of standards. And as far as the ITU is concerned, the G.711 codec is the same one as we were just discussing for doing 64 kilobit per second streaming continuous analog digital conversion and coding. There are 2 flavors of this, of course, one for North America and one for Europe. When we talked about 256 steps of value that we code the value of the sample into, well, those steps are not evenly spaced. We make the steps much finer around 0 volts and then grow the size of the step exponentially as we get away from 0 volts. And this helps us a tiny bit with noise. In North America, we use a method of growing the size of the levels called mu-law, and in Europe they use one called A-law. But these are just details. The G.711 codec spits out 64 kilobits per second, and it ends up with a mean opinion score of 4. If we want to start talking about other codecs, other algorithms for doing coding of the digitized speech, we're always comparing them to the 64 kilobit per second. And what we end up seeing is that there's a trade-off between reducing the number of bits per second you transmit, the delay that's introduced by doing this, the complexity of the algorithm and hence the horsepower of the processor you need to be able to do all the mathematical calculations in real time, and finally the resulting quality of the speech. Often what we find is that you can squeeze 2 or 3 of these different parameters, but it's very hard to squeeze all 4 of them all at the same time. And so we always end up with trade-offs between the different techniques. When we say voice compression, what we mean is compared to 64 kilobits per second. Are we using fewer bits per second? Another aspect to codecs is the question as to whether they're variable rate or constant rate. Constant rate means that they spit out bits per second, second after second, regardless of whether squeaking noises are coming out of your face or not. A variable rate codec only spits out bits if squeaking noises are coming out of your face. Now, this is one of the ideas behind being more efficient in terms of communications, is to have coded voice where we don't actually send any bits if there are no squeaking noises coming out of people's faces. And the statistics are that during a phone call, 40% of the time squeaking noises are coming out of your face, 60% of the time squeaking noises are not coming out of your face. So if we use a variable rate codec, then we're going to get some pretty significant efficiencies in using the backbone. In the voice over IP world, this is implemented with what's referred to as a voice activity detection flag. And so the codec can flag whether voice activity is happening or not, and then we can use that to decide whether to actually transmit packets or not. Now, in theory, this is all fine, but the problem is background noise. Because at the far end, when we're trying to reconstruct the signal and an analog on wires to put into a speaker to turn it into sound pressure waves that somebody's listening to, if we don't transmit any information when no squeaking noises are coming out of the speaker's face, what do we put on the line at the far end? Dead silence? I don't think that's going to sound very good. You can hear this on some voicemail systems. You're listening to a message, and while the person's speaking, you can hear all the background noise, and if they stop speaking, it goes dead quiet. I've heard this a number of times on voicemail systems, and it's a bit disconcerting. So you can start to think of all of the fun research projects we could have as to what do you put on the line when we don't have any information to put on the line. And we could come up with different models depending on where the person is. Like if they were in New York City at a phone booth, you hear all the people honking their horns and swearing at each other. Well, we'd have a little library of sounds like that, and we'd play it on the line during the silent intervals. Or you're out in the country, you'd have crickets chirping and things like that. What we might then realize is that perhaps we could have either just a library of hissing sounds, and believe it or not, we did that on regular transmission systems at the beginning because people didn't like the way it was so quiet when we went to digital transmission. But maybe we'd have an adaptive system that would listen to what the noise on the line was, and then it would reproduce that during silent periods. So this is a bit of an issue with variable rate vocoders. But this is the way that we actually get efficiencies, is to use that voice activity detection flag and not transmit packets when there's no voice activity. One of the older techniques that's been used in the telecom business for a long time is called ADPCM, Adaptive Delta Pulse Code Modulation. And if we take a look at our chart here, it's on the fourth line, the G722 series of standards. What this technique does is allows us to reduce the bit rate down to 16 kilobits per second. So people would call that 4-to-1 compression, because if you're only using 16 kilobits per second, then you could put 4 of those in a DS0 channel, 4 of those in a 64 kilobit per second transmission channel. So it's 4-to-1 compression. And the delay is 125 microseconds, 0.125 milliseconds. This is what we have in regular